Good morning, dear students. So, today, before we begin our lesson, let me tell you the portion for the unit test. We are going to have chapter number 2, Work and Energy, and chapter number 6, Classification of Plants for unit test 1. The questions will be of multiple choice questions, that is MCQ. Out of the 4 alternatives, you have to choose the correct alternative and write the answer. Okay, so now let us begin with chapter number 4, Measurement of Matter. In this chapter, we are going to study laws of chemical combination, atom, its shape, mass and valency, molecular mass and the concept of mole, concept of radicals. Now, let us go to the next slide. Now, in this slide, certain portion is deleted in this chapter, which I will be telling you. Now, here, can you recall the first 3 questions? They are deleted. In the previous standard, we have learned that compounds are formed by chemical combination of elements. We have also learned that an important principle of Dalton's atomic theory is that the molecules of a compound are formed by joining atoms of different elements. Now let us see what do you mean by laws of chemical combination. The composition of a substance changes during a chemical change. The fundamental experiments in this regard were performed by scientists in the 18th and the 19th century. While doing this, they measured accurately the substances used and formed. The scientists Dalton, Thomson, and Rutherford studied the structure of the substances and the atom and thus discovered the laws of chemical combination. Scientists could then write the molecular formulae of various compounds on the basis of Dalton's atomic theory and the laws of chemical combination. Here, we shall verify the laws of chemical combination by means of known molecular formulae. Try this. Now, let us see what is the apparatus here. Apparatus, conical flask, test tubes, balance, etc. Chemicals, calcium chloride CaCl2, sodium sulfate Na2SO4, calcium oxide CaO, water H2O. Activity 1. Take 56 grams of calcium oxide in a large conical flask and put 18 grams of water in it. Observe what happens. Measure the mass of the substance formed. What similarity do you find? And write your inference. Activity 2. Take a solution of calcium chloride in a conical flask and a solution of sodium sulfate in a test tube. Tie a thread to the test tube and insert in the conical flask. Seal the conical flask with an airtight rubber cork. Weigh the conical flask using a balance. Now tilt the conical flask so that the solution in the test tube gets poured in the conical flask. Now weigh the conical flask again. Now let us see what is given more in the slide. Now here laws of chemical combination. In 1785, the French scientist Antoine Lavoisier propounded the law of conservation of mass. In a chemical reaction, the total weight of the reactants is the same as the total weight of the products formed due to the chemical reaction. Total mass of reactants is equal to total mass of the products. Now, let us go to the next slide, page number 47. Now, in the picture above, you can see verification of the law of chemical combination. Here in the flask, calcium chloride is given and a solution of sodium sulfate is in the test tube and total weight is 300.23 grams. And after mixing, after the reaction, a white precipitate of calcium sulfate is formed in NaCl solution. Still, the weight remains the same, 300.23. So, this is law of conservation of matter. Now, in the above activities, the mass of the original matter and the mass of the matter newly formed as a result of the chemical change are equal. In 1785, the French scientist Antoine Lavoisier inferred from his research that there is no rise or drop in the weight of the matter during a chemical reaction. So, in a chemical reaction, the total weight of the reactants is the same as the total weight of the products formed due to the chemical reactions, and this is called as a law of conservation of matter. So you can mark the definition, this last 2-3 lines, you can mark it. Okay, now let us see what do you mean by law of constant proportion. Before that, this blue box is there, and introduction to scientists, it is deleted portion. It is included, it is not included, okay, it is deleted. Now let us see what do you mean by constant law of proportion, that is law of constant proportion. In 1794, the French scientist J.L. Proust stated that the law of constant proportion as the proportion by weight of the constituent elements in the various samples of a compound is fixed. So you can mark this law and you can learn it. Example, the proportion by weight of hydrogen and oxygen in water is 1:8. This means that 9 grams of water is formed by a chemical combination of 1 gram of hydrogen and 8 grams of oxygen. Similarly, the proportion by weight of carbon and oxygen in carbon dioxide is 3:8. For example, in 44 grams of carbon dioxide, there are 12 grams of carbon and 32 grams of oxygen. So that the proportion by weight of carbon and oxygen is 3:8. Now, how do you get this? Now, this is 3 plus 8 means 11. So, 44 grams upon 11, that is 11 fours are 44. So, 4 into 3 is 12. So, 12 grams of carbon, and 8 into 4 is 32. So, 32 grams of oxygen. Now, let us see here in the slide that in 1974, the French scientist J.L. Proust propounded the law of constant proportions. The proportion by weight of the constituents in the elements of various examples or samples of a compound is fixed. For example, water obtained from any source will have the same two elements, hydrogen and oxygen, present in it. 2 grams of hydrogen and 16 grams of oxygen form a molecule of water. The proportion of hydrogen and oxygen is 1:8 by mass. This proportion will always remain the same irrespective of the source of water. Now let us go to the next slide. Now, in this slide, the blue box you can see it is fully cancelled. So please cancel that in your notebook. It is deleted portion. Now let us learn what do you mean by atomic size, mass and valency. Now here, can you recall the first two questions? Yes, those two are deleted. Now, we have learnt that at the center of an atom is the nucleus, and that they are moving electrons in the extranuclear part. The electrons are negatively charged elementary particles, while the elementary particles that make up the nucleus are positively charged protons and electrically neutral neutrons. Look at the image of the atom obtained with a field ion microscope. So in that picture you can see, in this it is of iridium atoms. Every spot in this image is an atom. Now, the size of an atom is determined by its radius. The atomic radius of an isolated atom is the distance between the nucleus of an atom and its outermost orbit. And atomic radius is expressed in nanometers. So you can mark that nanometers. Now 1 upon 10 raised to 9 meters is equal to 1 nanometer, and 1 meter is equal to 10 raised to 9 nanometer. Now in the table you can see the approximate size of the atom. Atomic radius is given in meters, and example 10 raised to minus 10 is hydrogen atom. The size of water molecule is 10 raised to minus 9, and hemoglobin molecule it is 10 raised to minus 8. Now let us see a video based on atomic size.
Atoms are simply defined as the smallest indivisible part of any matter. That means atoms are very small in size. How can we say this? If we take the same example of a wall, then all the bricks that make up the wall are always small compared to the complete wall, right? Similarly, basic units that form a particular matter are always small compared to the complete substance. Now tell me, how big or small do you think a single atom will be? Maybe we can take another small entity and then compare the atom to it. Can we think of an ant? Probably not. Okay, so ants carry little grains of sugar? It means grains are smaller than ants. So maybe we can take a grain of sugar. How about a sand grain, which is smaller than the grain of sugar? But we can still see a grain of sand with our naked eyes. So can you tell me something smaller than this? Yes, we know that microorganisms like bacteria are tinier than what we can imagine, because we cannot see them with our naked eyes. So is an atom as small as a bacterium? You will be amazed to know that a single cell like a bacterium is made up of millions of atoms. Astonished, right? But the fact is that the bacterium can be observed at least using a microscope. However, seeing a single atom is nearly impossible. Yes, the size of an atom is that small. So that means there will be no units to measure it either, right? No, that's incorrect. In spite the fact that it's so tiny, we still measure the size of an atom with atomic radius. The radius of an atom is measured using units like nanometers. Wait a second. Do we know what a nanometer is? In simple words, 1 over 10 to the power 9 meters gives us 1 nanometer. So does that mean 1 nanometer is 10 to the power negative 9? Yes, that's how small a nanometer is. And atoms are measured in nanometers. So imagine how small they will be. Now let's take an example of a hydrogen atom. The atomic radius of a single isolated hydrogen atom is around 5 times 10 to the power negative 11. That's like 0.05 nanometers. Amazingly tiny. Now tell me, if atoms are so small, why do we need to study them at all? Needless to say, they make up the entire globe. Yes, everything that we see around us is made up of atoms. Even our body is made up of atoms. So studying atoms in detail becomes necessary despite their small size. Now, if they are so small, do you think they will have any mass? Think for a moment. If we say that atoms come together to make up matter, and if matter always has mass, it means atoms must possess at least some amount of mass. Yes, although atoms are very tiny, they do have some mass. But how do we calculate the mass of a single atom? Is it practically possible to do so? Is there any weighing scale available to weigh the mass of a single atom? If not, can it be designed? Let's find that out in our next video.
Okay, I hope you have understood the concept of the atom size and all. Now let us see on the next slide. You can see the top two blocks, that is square. The orange one and the purple one is deleted. Okay, so now let us see the concept of mass of an atom. Now the mass of an atom is concentrated in its nucleus, and it is due to the protons P and the neutrons N in it. The number of protons, that is P plus N, is the atomic nucleus, is called as the atomic mass number. Protons and neutrons are together called nucleons. So you can mark this definition, these two lines. Now, an atom is very, very tiny. Then how do we determine its mass? Scientists to struggle with this question. It was not possible for the scientists of the 19th century to measure the atomic mass accurately. Therefore, the concept of relative mass of an atom was put forth. A reference atom was required for expressing the relative mass of an atom. The hydrogen atom, being the lightest, was initially chosen as the reference atom. The relative mass of a hydrogen atom, which has only one proton in its nucleus, was accepted as 1. Therefore, the magnitude of the relative atomic masses of various atoms becomes equal to their atomic mass number, that is P plus N. Let us see how to express the relative mass of nitrogen atom having accepted the relative atomic mass of hydrogen as 1. The mass of one nitrogen atom is 14 times that of hydrogen atom. Therefore, the relative mass of a nitrogen atom is 14. This is how the relative atomic masses of various elements were determined. On this scale, the relative atomic masses of many elements came out to be fractional. Therefore, in the course of time, various different atoms were chosen as reference atoms. Finally, in 1961, the carbon atom was selected as the reference atom. You can underline that. In this scale, the relative mass of a carbon atom was accepted as 12. The relative atomic mass of one hydrogen atom as compared to the carbon atom becomes 12 into 1 upon 12, that is 1. The mass of one proton and one neutron on the scale of relative atomic masses is approximately 1. Now let us see this table. Now the relative atomic masses of some elements in the chart are given below. You have to find the relative atomic masses of the others. So you can take your pencil and you can write where there are blanks. I will be telling you. So the elements are given and the atomic mass. Hydrogen 1, helium 4, lithium 7, beryllium 9, boron 11, carbon 12, nitrogen 14, oxygen 16, you can write 16 there, fluorine 19, neon 20, sodium 23, write 23 there, magnesium 24, aluminium 27, so you can write 27, silicon 28, phosphorus 31, write 31 in the blank, sulfur 32, chlorine 35.5, argon 40, write 40, potassium 39, write 39, calcium 40. Now on the same slide you can see here some of the atomic masses of some elements are given in Daltons. You can go through it later on. Okay, now let us go to the next slide. So today we have highly accurate methods for measuring the mass of an atom directly. Hence, instead of relative mass, unified mass is now accepted as the unit of atomic mass. It is called as Daltons. Its symbol is U. Yeah. Now, 1 Dalton is equal to 1.66053904 into 10 raised to minus 27 kg. Okay. So now we will be seeing two small videos.
Chemistry gives answers to many queries. It acts as a bridge between the theoretical concepts and the practical world. However, where does chemistry get all the answers from? How do the reactions change everything around us so drastically? Well, the answers are stored inside the small nuclei of atoms. Yes, the tiny nucleus inside every atom is like a treasure box. It holds the mystery of several reactions. Now the next question to pop in our mind is, how does the nucleus of a single atom define the reactions in which the atom is participating? That's right. It's the subatomic particles in the nucleus, the protons and the neutrons that are the influencing factors. Yes, the presence and the number of protons and neutrons in the nucleus of any atom define many important characters like the atomic number, atomic mass, isotopic forms, and so on. Wait a second. Do we know what these are? What do we mean by atomic number? How is it different from the atomic mass, and what exactly are isotopes? Let's begin with the atomic number first. Atomic number is denoted by the letter Z. As the name suggests, atomic number means the number assigned to a particular atom. Now I want you to think, on what basis should an atom be assigned a number? Should it be on the basis of when the atom was discovered, or on the basis of how much quantity of the element is present in nature? what factor can be applied for numbering the atoms or the elements in general? One promising way is by numbering based on the number of protons present inside the nucleus of the atom. Yes, it's because the atom of every element has fixed number of protons in its nucleus. And this number is unique to every element, right? What do we mean by this? For example, any atom of oxygen always has 8 protons in its nucleus. No other element has atoms with 8 protons in it. That means the number of protons in the nucleus of an atom is like the identity of that element. So can we number the atoms or elements based on the number of protons in the atomic nucleus? Yes, this is how atomic numbers are defined. Atomic number, in simple words, is the number of protons present in the nucleus of the atom. Why do we need an atomic number, by the way? The atomic number helps in defining the characteristics of the element. And why so? Just think about it. We know that the number of electrons is equal to the number of protons in an atom. We also know that the number of electrons will determine the valency and thus the reactive capacity of an atom. So now can we connect the dots? Yes, the characteristics of elements will include a few properties. And these properties will be based on the reactivity of the atoms, right? We also know that the reactivity depends on the number of electrons present in the atom. And the number of electrons is the same as the number of protons. So this is why the characteristics of atoms are largely dependent on the atomic number. That is the reason the atomic number, or simply the number of protons, is important to us. Well, we know that atoms are the fundamental units of every matter. So can you guess what could the size of a single atom be? And do all the atoms of different elements have the same atomic size? Let's study the concept of atomic size in detail in the next video. In the previous video, we have seen how atomic mass is measured. Now let's understand atomic mass in detail. Before that, can you tell me what exactly the concept of atomic number is? Can you define it once for me? Yes, it's simply the number of protons present inside the nucleus of an atom. Now on similar lines, can you tell me what atomic mass could be? Yes, it simply means the mass of an atom. But how does it get determined? Imagine we have a bag which is made up of extremely thin material. So thin that it almost does not have any mass of its own. Now we fill this bag with some stuff inside. If this bag is placed on a weighing scale, then can we say that the total mass of the bag will be the sum of the mass of all the objects inside it? Absolutely. Similarly, the mass of an atom can be calculated with the help of the subatomic particles in it. But we know that among all the subatomic particles, electrons have negligible mass. That is, they are considered to be almost weightless. So what are we left with? Yes, we have both protons and neutrons in the nucleus. And these two do have some amount of mass is what we know. Now tell me one thing, which among these two particles should be considered? Shall we consider only the mass of protons or only the neutrons? Or both together? Well, since both have a significant amount of mass, we will consider the mass of both together. Hence, the atomic mass is defined as the total number of protons and neutrons present inside the nucleus of the atom. It is also referred to as the mass number. Let us take a simple example. In case of a simple element like fluorine, we find that there are 9 protons and 10 neutrons in the nucleus. Wait a second. We have always come across cases where the atomic nucleus has an equal number of protons and neutrons. So how is it that the number of neutrons is more? Well, tell me, does the presence of additional neutrons really bother the atom? Does the charge of the atom increase or decrease? Absolutely not. That's because they're neutral. Then why should an extra neutron bother us? So coming back to the atomic mass of fluorine, we have 9 protons and 10 neutrons. That means the total would give us 19. So can we say that the atomic mass of fluorine is 19 units? That's right. Just like fluorine, even aluminium has an extra neutron compared to the number of protons. That is, in a single atom of aluminium, we have 13 protons and 14 neutrons. Summing up the two, we get 27 units, which is the atomic mass of aluminium. Now let's take another random example of chlorine. A chlorine atom has 17 protons and 18 neutrons. That means the atomic mass of chlorine will be 35 units, right? Absolutely. But wait a second. A few chlorine atoms that exist in nature exhibit a different form. Some of them have 17 protons and 20 neutrons. That gives us the atomic mass of chlorine as 37 units. So which one is the correct atomic mass? In case of chlorine, both the atomic masses are right. The atoms having 17 protons and 18 neutrons have an atomic mass as 35 units. On the other hand, chlorine atoms with 17 protons and 20 neutrons have an atomic mass of 37 units. But now the next question to pop up in our minds is, how can we have one element having two different kinds of atoms? And is this valid only for chlorine, or are there other elements also which exhibit this phenomenon? Let's find out more about this mysterious concept of isotopes.
Okay, children, you have understood the concepts and the videos which were shown to you. Now, let me once again tell you the portion for the unit test 1. Chapter number 2, work and energy, and chapter number 6, classification of plants. You are going to have multiple choice questions. 4 alternatives will be given to you and you have to choose the correct one and write the answer. So please study for the exam. Okay, thank you.